Hey guys, today I want to share with you a little problem that I worked one afternoon when I was an undergrad. This is a problem I had a lot of fun with because it's not a problem that was assigned to me. It's something I kind of looked into on my own, and it ended up being a lot of fun. So what happens usually in a math class or a proof-based math class is you're usually told a result and the class works to prove the result. You get a theorem, let's prove it. And that's all well and good, but that's not really how mathematics is developed. Because before we can try to prove something, someone has to suspect that it's even true in the first place. It's not as though some, benevolent God comes to us and gives us a theorem to prove, although that would be awesome. The reality is that before it can be suspected, someone has to find a pattern. And if they find a pattern and it's interesting, then one can make a conjecture and attempt a proof. And that's kind of what I did that afternoon. So what I love about this problem so much is that it starts with an observation that a lot of people make, and it generalizes to a very nice statement, and the statement's pretty easy to prove. This only requires a little bit of trig and calculus. So what observation am I talking about? I'm talking about the observation that's made by a lot of calculus students, that the derivative of the area of the circle is the circumference of the circle. Just a quick application of the power rule and you'll see that the derivative of the area, pi r squared, is 2 pi r, which is also the circumference. This fact is pretty intuitive given the way that differentiation, integration, area are all connected. But if you check this with other shapes, you'll quickly see that it does not work. For example, if you look at a square with a side length of x, we know that the area of this square is given by x squared. And the perimeter of this square is given by 4x. So clearly, if we take the derivative of the area, we're going to get 2x, which is not the perimeter. So it doesn't look like this relationship is going to hold for other regular polygons. The thing is, though, that we do make a choice whenever we express the formulas for area and perimeter of this square. We're choosing to express these formulas in terms of the side length of the square. It's only the natural thing to do, but we don't really have to do that. We could choose to express these formulas in terms of some other measurement of the square. For example, we might choose to express the area and perimeter in terms of the length of the diagonal. There's nothing wrong with doing that. So the question is, can we find a measurement of the square so that when we express the formulas for area and perimeter in terms of that measurement, can we make the derivative of the area equal to the perimeter? Well, that's the question I asked. So here's how I answered that question. Although I don't know what measure of the square is going to make the derivative of the area equal to the perimeter, I do know that I can probably express it as some constant multiple of the side length. So let's define a new measurement of the square to be some constant multiple of the side length. So we'll say that r is alpha times x, so that x is r divided by alpha. So now we'll create new formulas for area and perimeter in terms of r instead of x. So the perimeter, which we'll call p bar of r, we know that it's 4 times x, so now it's 4r over alpha. And the area, which we know to be x squared, we'll call that a bar of r. We know that that's going to be equal to r squared over alpha squared. So now what we'll do is we'll just take the derivative of a bar and set that equal to p bar. That'll allow us to solve for alpha. So the derivative of a bar is just a simple power rule. We're going to get a bar prime of r equals 2r divided by alpha squared. And we're going to set that equal to p bar of r. Now with a little bit of algebra and a couple of cancellations, we can see pretty quickly that alpha is 1/2. So that tells us that the measurement we were looking for is 1/2 of the side length x. So r is 1/2 of x. So we can conclude that when we express the formulas of a square for area and perimeter in terms of half of its side length instead of its side length, then the derivative of the area is going to equal the perimeter. So that's a pretty interesting example of this working, but it's not really enough for us to come to a general pattern. So the next thing I did was tried another example. I tried the equilateral triangle. Alright, given an equilateral triangle of side length x, the area of the triangle is given by root 3 over 4 times x squared. And the perimeter is of course given by 3x. So we're going to proceed exactly like before, and we're going to call r some new measurement, and it's going to be equal to alpha times x. So we'll define our new functions. So a bar of r, so before we had x squared, so now we're going to have, well, x first of all is r over alpha. So we're going to have root 3 over 4 times r over alpha squared, which is root 3 over 4 times r squared over alpha squared. Right, and then p bar of r is going to be 3r over alpha. So like before, we're going to take the derivative of a bar and set it equal to p bar. The derivative here is again a simple power rule. We're going to get that a bar prime of r is equal to root 3 over 2 times r over alpha squared. And now we'll set that equal to p bar. We get that 3r over alpha equals root 3 over 2 times r over alpha squared. And so we'll start doing some cancellations again. R is gone and we have an alpha here, so we're going to have 3 equals root 3 over 2 alpha. And solving this for alpha, we're going to get that alpha is equal to root 3 over 6. So our new measurement that we want is root 3 over 6 times the side length x. Now, that may seem like a completely random result, a very strange result, and I thought it was too. But when I found this, I was lucky enough that someone in the room where I was working knew what this was. This is the radius of the inscribed circle of an equilateral triangle. Why he had that memorized, I still to this day have no idea, but I'm glad he did. So the result for the equilateral triangle is that when we express the formulas for area and perimeter in terms of the radius of the inscribed circle, then the derivative of the area is equal to the perimeter. So to recap, here's the two results we got from the examples we looked at. So the question is, from this information, can you extrapolate this to a pattern and make a conjecture? Right, so in both cases, the measurement we were looking for was the radius of the inscribed circle of this regular polygon. It's just that in the case of the square, getting half the side length, there's really no reason to think of that as, oh, that's the radius of the inscribed circle of the square. It's just half of the side length. But once we saw that weird measurement for the triangle that happened to be the radius of its inscribed circle, it's clear that that's how we want to view this measurement. So our conjecture that we can make, given this information, is that given any regular polygon, if we express the formulas for area and perimeter in terms of the radius of the inscribed circle of that regular polygon, then the derivative of the area is the perimeter. So that's a very nice and beautiful conjecture. The next step is to try to prove it. So here's how I ended up proving this. First, observe that any regular insided polygon can be divided into n isosceles triangles. The base of these triangles is the side length of the polygon. The angle on the inside is 2 pi over n. And the height of these triangles is r, the radius of the inscribed circle. So this is enough information for us to express formulas for area and perimeter in terms of the radius inscribed circle for the general insided regular polygon. So let's just grab one of these little triangles. So what we want to do at this point is to express x in terms of r and then find the area of this triangle in terms of r. So to get x in terms of r, let's look at half of this triangle. Just split like that. Then we know that the tangent of pi over n is equal to 1/2 x over r. And so x equals 2r times the tangent of pi over n. Now we want to find the area of the triangle. Well, the area of the triangle is of course 1/2 base times height. So that's 1/2 of x times r. But we just found that x is 2r tangent pi over n. So we get 1/2 times 2r tangent pi over n times r, which is r squared tangent of pi over n. Okay, so what does this say about the whole polygon? Well, the area of one of these triangles is r squared tangent pi over n, and x is 2r tangent pi over n. So the perimeter of the polygon is 2nr tangent pi over n. We'll call that p bar sub n of r. Whew, that's a lot of syllables. And then we have a bar sub n of r is nr squared tangent of pi over n. Now, recognize how powerful these formulas are. This gives the area and the perimeter of any regular n polygon in terms of the radius of its inscribed circle. So now the only thing to do is to check that the derivative relationship holds. So we differentiate a bar sub n with respect to r, and it's very quick to see that it does work. A sub n bar prime of r is a quick power rule, so we get 2nr tangent of pi over n. I don't know why I put those parentheses, but it's too late. We're committed. This is precisely p bar sub n of r. This completes the proof. We've expressed the formulas for area and perimeter of an arbitrary regular insided polygon in terms of the radius of its inscribed circle. And we showed that when we differentiate that formula for area with respect to r, the radius of the inscribed circle, we do, in general, get p bar sub n, the perimeter, with respect to the radius of the inscribed circle. Now, these formulas are really quite nice, so I'm going to leave this video off with a challenge for you. I want you to take the limit as n approaches infinity of these formulas and see what they become. The answer is not surprising, but it's still pretty awesome. If you find the answer, please leave your solution in the comments of this video. But that's gonna have to do it for this one. I'll see you next time.
Sorry, 93, I even got it tatted on me. 2012, lady, y'all not feeling sorry. And you know me, without T there probably would be no me, dog. Holler back at me in 2023. Line you bitches up from the nosebleeds, yeah. God's plan.